For both turbulent and laminar cases, we can see that the velocity is zero at the surface of the plate. This is caused by the no-slip condition, which explains that a fluid is stationary at the face of a surface. This stationary layer of fluid produces a friction force against layers above it. At points further from the plate, the effects of this friction force become less pronounced and eventually it disappears as the free stream is reached. In the graph on the left, we can see that the turbulent flow reaches free stream at a far greater distance from the plate when compared to the laminar flow case. This is caused by the friction at the plate surface. The greater the velocity, the greater the shear force applied to the wall. Since the turbulent case has fluid that is 30 times faster, this causes greater friction forces between the fluid layers and therefore a larger boundary layer. In the dimensionless graph on the right, we can see that even when the magnitude of flow is equal, the turbulent case still has a larger boundary layer. This is because a turbulent flow is moving in 3 dimensions and does not behave in uniform layers. This mixing of velocities results in a broader velocity profile when compared to the laminar case. We can see that the temperature graph behaves similarly to the velocity graph. The laminar case is an almost linear trend of cooling until it reaches the free stream where a constant temperature is achieved, whereas the turbulent case has a larger boundary layer as fluids of different temperatures are constantly mixed together and the transition to free stream is not as steady. This larger turbulent boundary layer causes colder parts of the fluid to move closer to the surface of the plate. This causes a greater temperature difference, which results in greater heat transfer. These 3 graphs show the relationship between the relative thickness of the velocity boundary layer and the temperature boundary layer. For air, its Prandtl number is 0.77. Material A's is 1 and material B's is 2. The Prandtl number is a ratio between a fluid's ability to diffuse momentum and its ability to diffuse heat. For air, we should see a larger boundary layer for temperature, as it has a greater thermal diffusivity than momentum diffusivity. Material A should have equally sized boundary layers, as its ratio is 1. Material B should have a larger velocity boundary layer, as it favors momentum diffusivity. Our actual results do not align with these expected results, as all the graphs seem to have relatively equal boundary layer sizes. For this difference to be visible on the graphs, there would have to be a much greater or much lower Prandtl numbers. This graph shows the results of 3 different methods to determine the heat transfer coefficient at different points of the plate. The first method is using the Fluent software. The next method was using the equation for local heat transfer coefficient, and the final method was using the Reynolds analogy. All 3 methods produce practically the same results as seen on the graph. For this case, any of the methods can be used. However, for more complex cases, using the Fluent software would be beneficial, as the computer would handle the complex mathematics. The Reynolds analogy is a useful method as it allows the heat transfer coefficient to be calculated from a known velocity profile.
Hi, I'm Drew. The following graph shows the heat transfer coefficient of the turbulent profile, and as we can see, it is much higher than that of the laminar in the previous slide. Since the molecular collision is so much more volatile than in laminar flow, initially the heat transfer coefficient is much higher. However, as the boundary layer grows, the heat transfer coefficient decreases in an exponential fashion as seen on the graph. All methods for calculating the heat transfer coefficient provided a very similar display on the graph. For this combined profile, the laminar flow ends at around 0.5 meters and the turbulent begins at around 2. This can be seen clearly when the boundary layer characteristics change as the flow transitions from laminar to turbulent. Initially, in the laminar flow, the boundary layer is growing, creating more distance for mixing molecules to travel. Once the boundary layer reaches a critical size, the flow changes to turbulent, where the molecular collisions are no longer orderly and instead chaotic and random, hence the growth in heat transfer. However, once this peak has been reached, the heat transfer coefficient begins to drop again in the flow direction. We can see that the purely laminar and turbulent profiles indicated in the dotted lines converge with their respective flow regions on the combined profile. While not as drastic as the change in heat transfer, we can see that skin friction coefficient also increases when transitioning from laminar to turbulent. This is due to the boundary layer no longer being smooth as molecules move in an orderly fashion. Instead, the boundary layer becomes rough as the collisions become chaotic and random. As such, there is more drag and skin friction. There is a direct correlation between the profiles for laminar, turbulent, and combined heat transfer coefficients and their total heat transfer and heat flux. Laminar is orderly and calm with the smallest heat transfer profile, and as such had the lowest total heat transfer rate and heat flux. Turbulent was the opposite, and the combined profile somewhere in the middle. This is a direct result of the heat transfer being interconnected with Nusselt's number and in turn Reynolds number. Laminar flow is known for having a low Reynolds number, and as such the results are as expected, and the same can be said for turbulent. Since the third profile was a combination of laminar and turbulent flow, it is understandable that it would be in the midground between the two other profiles.
Hi, I'm Stephen. The following three graphs will show the vector lines of the flow velocity with three different Reynolds number 1, 100, and 1 million. In the case of Reynolds number equal to 1, the flow through the cylinder is mostly laminar. The flow separation cannot be seen clearly due to the low Reynolds number. The wake region size is large and the flow is generally laminar. For Reynolds number 100, the flow separation can be seen clearly, and the wake region started to form vortex and becoming to be turbulent. In the Reynolds number 1 million case, the flow separation occurs much later than the Reynolds number 100 case due to the highest Reynolds number, and wake region is significantly smaller if compared with the Reynolds number 100 case. Flow separation occurs when the boundary layer on a surface becomes separate from the surface due to adverse pressure gradient leading to a region of recirculation and turbulence. This can occur at locations such as sharp corners, changes in the surface curvature, and adverse pressure gradients due to flow acceleration or deceleration. Flow separation may occur early or later depending on factors such as Reynolds number, the object shape, and surface roughness and flow condition. Flow separation patterns can have significant effect on heat transfer. The wake region can affect the local heat transfer rate, leading to variation in temperature distribution and heat transfer rate on the object's surface. Here's the graph for Reynolds number 1 case. The Cp versus radiant curve is smooth and separation point for this case is hardly noticeable. After the Cp value equals 0, the pressure becomes negative as shown in the pressure control. In the Reynolds number 100 case, the pressure dip is more significant. The separation point for the flow occurs somewhere at 100 degrees of the cylinder. The CP0 point occurs much sooner than the laminar flow case, which is supported by the pressure control. The Reynolds number 1 million case has much higher negative Cp value compared with the Reynolds number 100 case. This case also has the highest negative Cp value if look at the pressure contour. The lowest pressure point in the graph is much more lower than the surrounding pressure, which results in such negative Cp value. Also, if we compare the curve together, we can see that the separation point, which is the lowest point on the graph, is significantly delayed. The Cp value for three curves started at mostly the same point. However, the maximum negative Cp value is different, which is the Reynolds number 1 million case having the highest. The difference between the maximum and minimum Cp value is called delta Cp, is represent the size of the wake region.
For the following graph, skin friction coefficient, or CF, was plotted against the radiance value of a cylinder to display the fluctuating values of skin friction as flow passes around the cylinder. In this first example, where our Reynolds number is equal to 1, CF displays a parabolic shape on the graph. The skin friction reaches its peak at around 1.25 radians at a value of approximately 5, then decreases to 0. It should be noted that it does not have a second peak as there is no weight created. In the RE100 example, we see the CF value peak much earlier in the cylinder at 0.8 radians with a value of 0.4 before reaching 0 at around 2 radians. At this point, however, the value then increases again at 2.5 radians to 0.025. This is due to a wake being created behind the cylinder where the flow is recirculating. Lastly, in the RE10 to the power of 6 example, we see a peak at 1.4 radians with a value of 0.016, followed by a decrease to 0 at 2.4 radians, then a second peak at 2.8 radians with a negligibly low CF. Therefore, it can be deducted from the previous three graphs that as Reynolds number is increasing, CF is decreasing. This can be explained by the fact that as the Reynolds number increases, the flow becomes more turbulent, and as turbulence increases, drag decreases, and therefore so does skin friction. As can be seen from this video, fluid flow around a cylinder with a Reynolds number of 100 creates what is known as vortex shedding. This is where a low pressure region occurs behind a bluff body, an object in which there is a large amount of separated flow, in the form of a wake. As fluid passes around the cylinder, it recirculates in the wake, creating wave-like velocity patterns that exit off the body. These vortexes, due to their varying velocities, cause vibrations on the objects they pass, which can potentially match the natural resonance of the objects. These vibrations can then seriously damage the bluff body and should therefore be accounted for in their construction or reduced. Lastly, we compared the heat transfer of the cylinder with a Reynolds number of 100 and a Reynolds number of 10 to the power of 6. It can clearly be seen that the RE 10 to the power of 6 value has a much higher heat transfer than the RE 100 case due to the incredibly small boundary area. This is because as the RE number increases, the flow becomes more turbulent, which results in fluids mixing together, increasing the heat transfer due to convection.